In this video, we now want to tackle one of the more challenging problems for introductory students. This is the inclined plane problem, all right? And the inclined plane problem is typified by a box or a brick or some object, and it's sliding down an incline. And initially, we typically take the incline to be frictionless. Now, we haven't actually introduced friction yet, but we're going to state, okay, that for the purposes of this example, the incline is frictionless. Now, the goal of this inclined plane problem is to determine the acceleration that the object is sliding down the incline with. Now, a little bit of logic would tell you if I have a very shallow or slight incline and I let something, slide or roll down, it's not going to necessarily be a large acceleration as opposed to a large incline where something's going to be falling very rapidly. So at least initially we can get a sense that the acceleration that the object is going to slide down the incline with should be related to the angle. And the larger the angle, the larger the acceleration. And that's what we'll find happens, and that's what logic would dictate should happen, okay? Now, the way we set this problem up is that the flat bottom of your incline, okay, is always going to be assumed to be parallel with the surface of the earth. And that being the case, weight, the force of gravity, is always going to be pointing straight down toward the surface of the earth, all right? But what other forces are acting on my object? I know that my object is sliding down, but what else is happening? Well, in the previous couple of videos, we saw the normal force. If something is resting on a surface, then that surface is pushing up, normal to that surface. So now my surface is not parallel with the ground, it's at an incline, and that means that my surface must be pushing up perpendicularly to the surface. So if I draw a dotted line here that is perpendicular to the incline, there should be a force pointing up from that line that is perpendicular to that surface. We call this, again, this is just the normal force, but it's perpendicular to the plane now. And now notice, okay, since the normal force is perpendicular to the plane, my acceleration is parallel to the plane, it would make more sense to now define a new coordinate system. I don't necessarily want to put x in this direction and y in this direction. I don't necessarily want this, because then if I were to extend this out, I would have my acceleration coming off at some angle like this, and my normal force at a right angle to that, like this. And so my acceleration and my normal force would both have individual components, and I would have to figure out what those components were. It actually simplifies things if I rotate my coordinate system. So my x direction is typically horizontal, my my y direction is vertical. But what happens if I tip it? So that now my x direction is parallel with the plane and my y direction is normal to the plane. Well, now the acceleration and the normal force lie right along the axes. And that simplifies things. So I'm going to make a new coordinate system so that x is parallel with the plane and y is perpendicular to the plane. And you'll see how that simplifies some things. Now we still have to deal with the weight, okay? Now, the overall idea here is that the object is accelerating down the incline, and we want to know with what acceleration, okay? Well, we can start with the weight here, and now the weight, if I extend these coordinates down, my weight, if I displace this into this coordinate system, I see that it is downward like this, right? And so now what this is going to do is that my weight is going to have a vertical component here and a horizontal component here. So we're going to call this omega vertical, or not omega, but W vertical. And we can call this W horizontal. And you can prove to yourself that the angle, if I were to draw these components in my diagram here, that you can prove to yourself that this angle that your weight makes with the y-axis is also the angle theta. Okay, I'm not going to take the time to prove it, but you can do it with geometry. All right, so just take my word for it for now. Maybe I'll do it in the next video. We'll see. But what we can see, if this is theta, then my weight in the vertical direction, in the negative y direction, is just going to be my weight times the cosine of theta. And my weight in the horizontal direction is going to be my weight times the sine of theta. So this is just mg. So this is mg cos theta. And this is mg sine theta. Right? So that's mg sine theta. And technically these would have negative signs attached to them since they're both in the negative directions. In this case, positive x is pointed upward, y is pointed downward. Some people tend to put the positive x in the direction of the acceleration. It doesn't matter, okay? The magnitude of the acceleration is still going to remain the same. Now, how do we set up f equals ma for this case? What we want to do is set up f equals ma in each direction, in the y direction and in the x direction. So I want to know what my f net is in the x direction, and I want to know what f net is in the y direction. Now, here's the key, okay? In the y direction, it's not accelerating downward in the negative y direction, and the plane is not pushing up, the plane is pushing up, but it's not pushing up enough that the box jumps up in the y direction. So what's happening is that these two forces are balancing, okay? The normal force is being counterbalanced by the weight in the negative y direction, or mg cosine theta. So in the y direction, my f net is 0 because the box is not accelerating in the negative y direction or in the positive y direction as our coordinate system is defined. So in this case, the total force is 0, and that means that my normal force, which is in the upward direction, minus my mg cosine theta, must also equal 0. Okay? So what that's telling me is that my normal force then is equal to mg cosine theta. So if I want to know the magnitude that my plane is pushing up with, it's just equal to mg cosine theta. And if you think about it, that makes sense. The lower I make my plane, the larger cosine gets, and the closer and closer the normal force must be to the entire weight, mg. Whereas if I raise my plane, the incline is pushing less and less and less in the y direction as the box slides faster and faster and faster. So this formula makes some intuitive sense. And now you can see that in the y direction, or in the x direction rather, this is the only force, okay? I don't have anything pushing back up on my box, so this mg sine theta is the only force. So, and that is going to equal, and I'll do it down here, that is going to equal negative ma, since we're accelerating in the negative x direction here. And what we can see is that my m's cancel out since they're both the mass of the box, and my acceleration is equal to negative g sine of theta. So the acceleration the box experiences is going to be proportional to the sine of the angle. And that satisfies our thought that we had at the beginning of the video. The smaller the incline, the less the acceleration. The smaller this angle, the less this acceleration. The smaller this angle, the smaller the sine is. So as my plane gets smaller and smaller and smaller, the slower the box is going to accelerate down the incline. As I raise my incline to larger and larger angles, the object is going to slide faster and faster and faster because the angle increases, the sine of your angle increases as theta increases, all the way up to 90. All right, so this is how you find the acceleration down the plane, and the big key is rotating our axes so that they're parallel and perpendicular with the plane. All right, I hope that helps with the inclined plane, and we'll see you in the next video.